Okay, so we are in section 6.6. We're talking about applications to physics and engineering. And we are looking at that, how to see how calculus helps us. Chapter 6 deals with applications of integration. So 6.6 is applications to physics and engineering. And we already looked at 3 examples from the textbook on Monday, the first 3 examples from section 6.6. We talked about, well, first of all, we're interested in work problems. Okay, and Avery, I'll get to that question a little later. Okay, I'll get back to you on that. All right, so we found that work is the integral from A to B, okay, of your force function. So your force function f of x varies with respect to x, and x is essentially position. And let me give you a moment to copy this problem down. Okay, so in this problem, we have a 1,600-pound elevator, and the 1,600-pound elevator is suspended by a 200-foot cable that weighs 10 pounds per foot. We want to know how much work is required to raise the elevator from the basement to the 3rd floor, which would be a distance of 30 feet. Okay, so this problem, if you recall in example 3 from the textbook, we looked at a problem regarding work needed to lift a cable up to the top of a building. This problem is similar. It's just you're talking about bringing an elevator, raising an elevator 30 feet. So you're not bringing the elevator to the top of the building. The elevator is connected with the cable. You're not bringing the elevator to the top of the building, but you're moving it 30 feet. So what would be helpful in this problem to have? What would be a helpful thing? Well, so Jonathan, your total weight is going to be necessary. And even before you get there, what would be very helpful? What's helpful for all the problems so far you've seen in chapter 6? What's always helpful?
We need the formula for work.
Drawing it out. Yeah, drawing. We want to draw a picture out. So that's right, Claire. That's right, Victoria. We want to draw a picture. So I'm going to draw a picture here. I'm going to go to the next page here. Move to the solution. Are there any questions so far? Okay, now this problem, by the way, is a problem that is it's not in your, like an example in your book, but it's an additional problem, and I think it'll help you with like some of your homework problems. So, okay, let's go here. All right, let me give you a moment to copy this picture down, okay? Let me give you a moment to copy this picture down. So we're looking right here. We have an elevator here. And then over here, we have top of the building. Okay, let me give you a moment here. Okay, so let me highlight the cable in red. Here's the cable highlighted in red. And again, we are going to be moving the elevator 30 feet. Now in this case, there are three components to the work. Okay, three components to the work. And what I'd like to do is talk about each of the components piece by piece, okay? So first of all, let's talk about the elevator. The elevator weighs 1,600 pounds. And by the way, how is work defined? Simple work. What's the definition of simple work? Force times, that's right, Yalaton, force times distance. So we have two things to worry about here. We have the work needed to move the cable. You know, if we move the elevator 30 feet, the cable is going to move 30 feet. So we have the work needed to move that cable 30 feet. You know, the cable isn't going to move 30 feet on its own, right? You need a winch to do that. But also the elevator moves 30 feet. The elevator is very simple. The elevator is just like dead weight. And the work needed to move the elevator would be the force, 1,600 pounds. So pounds is a unit of force. The elevator weighs 1,600 pounds. So the work needed to move the elevator 30 feet is just 1,600 pounds times 30 feet. Okay. That takes care of the work for the elevator. But then we have to consider the cable. So for the cable, you have 200 feet of cable. And if we think about this cable here, maybe I'll just draw a little picture over here. No, I want it to be, okay, there's the cable. And we can split the cable up. We can split the cable up. Okay, you have the top 30 feet of cable. Okay, top 30 feet of cable. And then you have the bottom 170 feet of cable. Okay, so You have the bottom 170 feet of cable from here to here. And then you have the top 30 feet of cable from here to here. Now, to move the elevator 30 feet, the cable has to move 30 feet, right? Because the cable's attached to the elevator. So the top 30 feet of cable, does the top 30 feet of cable need to reach, the top of the building in order to move this elevator? I mean, here, I want to draw it kind of nice here. Okay, here's the top of the building right here. Does the top 30 feet of cable reach the top of the building if the elevator moves up 30 feet?
Professor, I have a question.
Sure.
So, how do we know that the top is 30 feet and the bottom is 170?
Well, the reason I'm doing this is I have to treat the top 30 feet of cable differently than the bottom 170 feet of cable. Because when you move the elevator up 30 feet, the cable moves up too, right? The top 30 feet of cable has to reach the top of the building, like on the winch. But the bottom 170 feet of cable doesn't reach the top of the building. So it can be treated like dead weight, just like the elevator. You see, the elevator is you're just moving the elevator 30 feet. Well, the bottom 170 feet of cable, you're just moving that up 30 feet too. You see? It's like dead weight along with the elevator.
Oh.
And how much would the bottom 170 feet of cable weigh? Well, you would take that 170 feet of cable right here and multiply it by 10 pounds per foot.
Professor,
and so that's going to get that bottom 170 feet of cable is going to weigh 1,700 pounds. You multiply 1,700 pounds by 30 feet, and that's going to give the work needed to move the bottom 170 feet of cable up 30 feet.
Professor, what I'm asking is like, how do we know that the top is 30? Like, how do we know it's 30 and not like 20, for example?
Well, because the distance that the elevator moves is 30 feet. If the distance that the elevator moved was 40 feet, then you would use 40 feet of top cable and right. Good question. Are there any other good questions?
Where did the elevator start again in this problem?
So in the problem, the elevator's at the very bottom. Let the elevator, well, I want to be, the elevator starts in the basement. So it's like in the very bottom, and it's just getting moved up 30 feet. Okay, so far, there are 3 components to computing the work. We have 2 of them. And now what we have to worry about is the top 30 feet of cable. So the thing you have to recognize is the top 30 feet of cable, we're going to need a Riemann sum to find the work. So why is this? Well, let's just look at the picture here. Okay, so, you see here I've drawn a piece of cable here that has a width of delta x feet. It's a small chunk of cable, and that's I'm going to call my first piece of cable. And then I've drawn another piece of cable here that also has width delta x feet, and it's located closer to the top of the building. Again, this is the top of the building here. So both pieces of cable, the one that's lower down and the one that's further up to the top of the building, they weigh the same because they're both have a width of delta x feet. But which piece of cable would require more work to bring to the top of the building? The first piece of cable there, and I'm looking at the picture here. The first piece of cable or the second piece of cable. First piece of cable is x1 feet from the top of the building. The second piece of cable is x2 feet from the top of the building. Which piece of cable is going to require more work to bring to the top? The first piece of cable or the second piece of cable? What do you think? So this is the first piece of cable here. Here's the second piece of cable.
I think the second.
Well, and I'm getting a variety of different answers. Which is always, nice and interesting. And I appreciate all answers. It turns out it's going to be the first piece of cable. Because remember what work is. What is work? Work. Well, both pieces of cable weigh the same. Both pieces of cable weigh the same. But that's right, Mark. The first piece of cable, the first piece of cable right here is further away from the top of the building than is the second piece of cable. So you see, what we're going to do with the top 30 feet of cable is we're going to treat that 30 feet of cable, we're going to slice it up into chunks of cable. So bringing up the top 30 feet of cable to the top of the building so the elevator can move 30 feet, that would be equivalent to taking that top 30 feet of cable and breaking it up into little pieces, and then bringing up each little piece separately to the top of the building. So if we can find an expression to represent the work needed in bringing a piece of cable to the top of the building, that's going to help. So, well, work is force times distance. This is now where the first part here comes into play. So first of all, we need, since work is force times distance, we need to know the weight of the ith piece of cable. Well, the ith piece of cable is delta x feet long, and it weighs 10 pounds per foot. So if we multiply 10 pounds per foot times delta x feet, the feet simplify out, and you're left with 10 times delta x pounds. Then we're going to multiply that weight by x sub I feet. We have to let x vary because different pieces of cable are, different distances from the top of the building. We add up then all these, and we add up all, these, this here's work, right? This 10 delta x times xi right here, that stands for work. Work to move the ith piece of cable to the top of the building. We have to add up all those pieces of work because we're taking the top 30 feet of cable and breaking up into little pieces. And we're going to add up the work needed to bring up each piece. And of course, our estimate of the true value of the work to bring up that top 30 feet of cable will be more accurate if we take smaller and smaller pieces of cable. So we let n go to infinity, and this is where the Riemann sum comes into play. So these are the three components that we need to do here. But of course, I mean, what would the first piece of work for the top 30 feet of cable? Okay, for the top 30 feet of cable here, what would that Riemann sum become as we take the limit as n goes to infinity? What's that going to approach? What always happens when you have a Riemann sum and you take more and more subintervals and let n, the number of subintervals, go to infinity. What always happens? What's the Riemann sum become? It becomes an integral. That's right, Yonatan. And it's going to be the integral of 10x dx. That's going to be your integral, 10x dx. And the limits, of course, are going to go from 0 to 30. 0 to 30. Are there any questions on that? Before we go to the next page? Yes, Clea.
So this first one with the limit, so it's kind of separate from the other two that they are down?
It is. It is separate. Yes.
Okay.
It is.
Okay. So we need to do all three of these parts, right?
Correct. That's correct. Yep. Okay. Are there any other good questions? Okay. Well, let's go to the next page then. So now the work, well, so the work needed to move the elevator 30 feet was 48,000 foot-pounds. That comes from taking 1,600 times 30. Okay, so let me just go, hold on, let me just go back for a moment. So this part here is 4,800, or no, 48,000 foot-pounds. And then this part here, if we take 170 times 10 times 30, okay, and we know the units are right because if we cancel the feet out and we're left with units of foot-pounds. So it's like in chemistry, you know, you kind of confirm your work by checking those units that they're right. Work units. That's 51,000 foot-pounds. So, and again, here, this part here becomes the integral from 0 to 30 of 10x dx. So that being said, here it is. And now we just compute the integral. The antiderivative of 10x is 5x squared. We put in 0 and 30 and work it out, and we're going to get 103,500 foot-pounds. All right, please let me know if you have any questions. All right, who's feeling, I mean, I know it's new material, but who's feeling, this is all right. Who's feeling reasonably okay, reasonably comfortable? Okay, Avery's okay, all right. Susanna, good. Okay, well then I'd like to do another problem here. So we will get our break here, but I think we should do another problem before our break. So, okay, let's talk about a tank. Let's talk about a tank here. So this is a tank problem. Okay, let me give you a moment to copy down, and there's a picture of the tank. There's a picture of the tank too. Okay, so let me give you a moment to copy that down, and then I'll discuss the tank a little bit. Hi, Susanna, you have a question. All right.
Hi, yes. On that last one, is there any reason you drew the top 30, you drew the 30 feet that elevator was moving in the top, even though the question was saying it was coming from the basement?
Well, see, to move the elevator 30 feet up, the cable has to also move up, right? 30 feet.
Okay.
So that's why you have the top, and that top 30 feet of cable has to, like there's a winch on the top of the building pulling that cable up. That top 30 feet of cable has to reach the top of the building.
Okay, I see.
And
So
to
that,
model that work, we need the Riemann sum, and that's why we split it, the work, split the
okay.
cable up. All right, good question. Good question.
Yeah, okay. Thank you.
Yeah, you're welcome. Jonathan says, won't the cable get lighter as it gets pulled? Well, as you pull the cable, the top 30 feet of cable, as you know, as the winch keeps turning, once the cable reaches the top of the building, the work's done on that. So the I want to say it's the right way. So I'm not so sure. The cable can't. There's less cable to pull up. Let's put it that way, Jonathan. Let's put it that way. As the cable gets pulled, yes, yes, that's right. All right, good questions. Good questions. Well, let's see what's going on here now. Okay, another kind of applied problem, a tank problem. So in this problem, we have a tank below that's full of water, and we want to find the work required to pump the water out of the spout. So here's the spout here. Here's the spout right here at the top. So when the water reaches the top of the tank, it flows out of the spout. We're told that water weighs 62.5 pounds per cubic foot. How many maybe have heard of that measurement for water, the weight of water? All right, Jonathan's seen it, and all right, so that's just a fact. And what am I doing here in my picture? So the tank is 6 feet high, and it's hold on here, 10 feet wide, but like, so what I've done here, what I've done is you might notice there's like a strip, so to speak. See this here? So what I'm going to do, let me use the line on it. So what I'm drawing here is what's called the ith layer of water. Okay, so this here is the ith layer of water. So just like with the cable, we broke the cable up into N pieces, the top 30 feet of cable in the previous problem. This problem, we're going to take the water and break it up into N layers of water. Okay, so, and what I've drawn is just a representative layer of water. And for this layer of water, that layer of water has a width, delta x. So the layer of water really resembles, it's like looks like a thin brick, okay, or a thin rectangular parallelepiped. It's like a thin brick. I mean, just think of this layer of water. It's a layer of water. It's going to be, how many have seen like those Hershey chocolate bars? I don't know if you've seen those like in the stores. They're really good. Flat. They look like a very thin kind of brick. That's what we have here. And what we want to do, of course, we know that we're going to have to find the volume of the ith layer of water. But the problem is, okay, here, I mean, this here length, let me just draw it a little better. Hold on here. I mean, for a box, say a box, how do we find the volume of a box? Do you remember the formula? Length, that's right, good. Length times width times height. And what we have here is an ith layer of water. It's a box of water. But the problem is we know the height is delta x. And we know the width is 10 feet. But we do not know what the length is. We do not know what the length is for that ith layer of water. And in order to find the volume, an expression for the volume of the ith layer of water, we need to find an expression for that length A. Mark, this, we're not dealing, I see what you're saying. You're thinking, Mark, like about a cross-sectional area, like the integral of a cross-sectional area. The problem is there's more involved here. So we're not just we're not finding the volume of, I want to say this the right way. We're not interested in finding the volume of all that water in the tank. We're interested in finding an expression for the volume of the ith layer of water in the tank. That's what we're, and you'll see why. Very good question. So what I'm going to do is I'm going to go to the next page and show you the solution on how we find this A value. Are there any questions? Any questions before we go to the next page? Okay. Okay, very good. Well, here we go. So what I've done is I've just redrawn the picture. And what I'm doing here is I'm looking at the side of the tank. Okay, and maybe I'll put it in blue. I'm looking at this side of the tank. This side of the tank. Okay, and that's what I've drawn here. Okay, and I have this ith layer of water. Okay, that has height delta x, and I'm interested in finding an expression for that length a. So what we have here is we essentially have two right triangles. You have the big blue right triangle there, which is the side of the tank, and then you have here, I want to draw it right, you have a smaller right triangle here. And I've drawn them both here. Let me give you a moment to copy that picture down. Okay, so here's that ith layer of water, and the ith layer of water is located a distance. Hold on, I gotta have it. It's located a distance x sub I from the top of the tank. This distance x sub I. But since the tank is 6 feet tall, the distance here would have to be 6 minus x sub I. Okay, so you can zoom that in a little bit. So you have x sub I here, and 6 minus x sub I here. And we recognize that the bigger triangle and the smaller triangle here are similar triangles, right? How many recall seeing similar triangles in maybe high school, in like a geometry class? Clea remembers it. Yeah, well, that's what we have here. We have similar triangles. These two triangles are similar. And that means that their sides are in proportion to each other. So if the smaller triangle, we were to take this side A and divide it by 6 minus xi, that would have to equal 12 over 6. And that gets us this proportion. What I shaded here is just the ith layer of water. That's what that is, OPME. I drew it kind of big, but it's just the ith layer of water. That's what it is. Okay, with height delta x. Okay, Clea, yes?
Professor, like as far as I remember, like when we do like with the proportion with similar triangles, isn't it supposed to be like A over 12 equals 6 over 6 minus x1, or?
Well, you could do that too.
Oh, okay.
Yeah, you could have A over 12 equals 6 minus xi over 6. Sure.
Oh, okay.
The proportion, if you think about like cross multiplying,
Mm-hmm.
the proportion's the same as this proportion.
Oh, okay.
And what we're trying to do is we're trying to find an expression for A. So, well, on the right side, 12 divided by 6 equals 2. No problem there. And then A would equal 2 times 6 minus xi, or A equals 12 minus 2 times xi. So now volume, which is length times width times height, that's going to be 12 minus 2xi. Okay, this is the volume for the ith layer of water. I'll call it V sub I. 12 minus 2xi times 10 times delta x, and they're all in feet, of course. Are there any other good questions on that?
Would we have to half it because it's a triangle?
I'm sorry, Susanna, would we have to do what?
Would we have to multiply it by 1/2 because it's a triangle or not?
No, we're not. We're not trying to find the area. Area of a triangle is 1/2 base times height, but we're only interested in the. We're interested in the volume. We're interested in the volume
Okay.
for the ith layer of water up here. We're interested in the volume, and now we know the volume. It's 10 times 12 minus 2 times xi times delta x. Okay, so this volume here that we're talking about, the volume of the ith layer of water, it's not connected to section 6.2. It's like a separate thing. All right, now that we have an expression for the volume of the ith layer of water, what might we want to do next? To find the work needed to bring the ith layer of water to the top of the tank, what do I need to find to compute the work? What do we need to know about that ith layer of water? The weight. Good, Susanna. Right, John. We need to know the weight of the ith layer of water, or the force. And then also, as John says, we need to know how far down the ith layer of water is. But based on our picture, the ith layer of water is xi feet. I'll just circle this, xi feet from the top of the tank where the spout is. So okay, let's go ahead to the next page. Now we know the volume of the ith layer of water, and I rewrote it. I have it as 10 times A times delta x. You could write it as A times 10 times delta x, whatever works, but this is good actually. 10 times A times delta x. John, we're going to be using foot-pounds for when we compute our work for this. We're not going to use Newton meters. We're not going to use joules. We're going to stick with foot-pounds. So you notice what I do is when I really get, okay, you're welcome. I see how I put in the units. I got feet here, feet here, feet here. And then when I multiply, I get cubic feet. And that tells me, hey, yeah, that's a volume. How many find that helpful in the work to like have the units in there. Okay, John's liking that, Mandy's liking that. Wonderful, wonderful. Okay, and Daniel and Avery, good, good. So, okay, well, now that we know the volume of the ith layer of water, we can find the force or weight of the ith layer of water. Because you see, the volume is the quantity 120 minus 20 xi times delta x cubic feet. But how much does that volume weigh? Well, we just multiply that by that volume by 62 pounds per cubic foot. And then what happens? What happens is the cubic feet cancel out, and naturally I'm going to distribute the 62.5 to the 7,500 and the 20 times xi, and this is going to give me then, let me see here, 7,500 minus 1,250 xi times delta x pounds. That's the weight of the ith layer of water. So the weight or force of the ith layer of water is dependent on x sub I, because x sub I determines how far down, x sub I is the distance, how far down the ith layer of water is from the top of the tank. So naturally, you know, because of the shape of the tank, the x sub I is going to come into play. Are there any questions up to here? Okay, well now we want to know the work needed to raise the ith layer of water to the top of the tank. What's the work needed to raise the ith layer of water to the top of the tank? Well, so again, what is work? Work is force times distance. The force we know, this is your force right here. And we're going to multiply that by the distance. This is the distance that the ith layer of water is from the top of the tank. It's xi feet. And so the work to raise the ith layer of water to the top of the tank, and naturally this x sub I I'm going to distribute on the 7,500 and the 1,250 xi. The work needed to raise the ith layer of water to the top of the tank would be quantity 7,500 xi minus 1,250 xi squared times delta x, and the units now are in foot-pounds. Please let me know if you have any questions. I'll stop for a moment. Yes, Susanna, yes.
Why did you square 1250 xi?
It's just the xi that's being squared. But why did I do that? How do I get that?
Yeah.
This xi here, I'm going to multiply it by 7,500.
Oh, I
by
see.
1,250 xi. Okay,
Oh,
good,
got it.
good. Okay, well then the total work to lift the top of the water to the tank is just the Riemann sum, where I goes from 1 to n, of where you have the work needed to bring each layer of water to the top of the tank. So I mean, if I were to write this out, this would be the limit. If I wanted to write this out here, this would be the limit as n approaches infinity of the summation, where I goes from, try it again here, hold on. Need a little bit of room. This Riemann sum I goes from 1 to n. And what's W sub I? It's 7,500 xi minus 1,250 xi squared delta x. And we're taking the limit of that as n approaches infinity. But then this here is going to become an integral, where your integrand is 7,500x minus 1,250x squared. And the limits go from 0 to 6. Okay, why does it go 6? So Clea, the reason is the tank, so the tank, well, if I just draw like the quick picture of the tank here. Okay, just the side of the tank. So the x-axis is measured here. This is your x-axis. And so here, at the top of the tank, the ith layer of water there would be at level x equals 0. Whereas here at the bottom of the tank, the ith layer of water would be at distance x equals 6 feet, you know, from the top of the tank. So and then all the other layers, they're somewhere between 0 and 6 feet below the top of the tank. Okay, very good, very good. Are there any other good questions? Okay, well then let's proceed on to get the answer, right? So we have an integral here that we have to compute to find the work, and there it is. We get the antiderivatives of each. So the antiderivative of 7,500x, right, is 7,500 times x squared over 2. But then that reduces to 3,750x squared. Okay, so hopefully everything you see here is pretty much common sense. How many think this is rather a fascinating problem? Being your ability now to do this kind of problem. And this is an engineering problem, right? I mean, how many think this is actually pretty cool? Susanna's liking it, Avery and Mark are liking it. It's really quite amazing. I agree. You know, Captain Kirk went up into space today, right? I don't know if he's 90 years old. He's the oldest gentleman to go into space. How many heard this? He went on, what's it called? Blue Orbit, or I think that's what it's called. How many have heard that? I heard it on the radio. You know, he wouldn't have gotten up into space, right, without calculus, right? I mean, Okay, Clay saw on the news. Franklin says it's cool, but too long. Oh, you mean he's too old to go up into space, or it takes. Well, when I'll just mention, when he did Star Trek, he was the first Captain Kirk for Star Trek. Very popular. You know, it's sort of befitting he went up into space. I think it's kind of cool. But yeah, Franklin, he waited a long time. Yeah, yeah, I understand. Um, all right. Are there any other questions before I stop the recording? Okay, I'll stop the recording.